So as previously mentioned, Hooke's law is special in that it is a linear relationship. So it does follow that form y equals mx plus b. So if we want to plot the applied force as a function of the displacement, we would get a straight line. And what we would find is that the slope of that straight line is actually going to be the spring constant. Because again, if I look at Hooke's law, if I look at F equals kx, well, if I plot the applied force on the y-axis and I plot x on the x-axis, well, we know from our formula, the equation of a straight line, y is equal to slope times x plus b. So what that's telling us here is that the slope will be the spring constant, and then in theory, b should be 0. If you don't apply a force, there shouldn't be any stretch or compression. So let's look at Hooke's law. Let's see what we got here. So we got a spring, it's stretched, and we have some values for the displacement from equilibrium, so that's good. We have this x value, and we have this applied force. What we'd like to do is we'd like to graph this, and we'd like to be able to determine the actual spring constant. So what we want to do is we want to plot our applied force on the y-axis. We want to plot our displacement on the x-axis. So we have a graph here. Well, with graphs, first thing we should have is a title. We could say applied force as a function of displacement. I'm just going to say displacement. No, I'm not even going to put the words from equilibrium. Or you could put applied force versus displacement. That works as well. You just want to make sure that there's a y versus x in your title, or y as a function of x, which means on my y-axis, we're going to put the applied force in newtons, and then on our x-axis down here, we are going to put our displacement. So with this, what we'd like to do is we'd like to set up a scale. Now my displacement goes from 0 to 0.6. I have 10 divisions here, so I'm going to go up by 0.1s. So this is going to be 0, this is going to be 0.1, 0.2, I should probably put the zeros for significant digits, 0.30, 0.40, 0.50, 0.60, 70, 80, and I probably couldn't get away. You don't have to label every tick, as long as it's clear what it's going up by. Like if I went 0 and then 0.2 on this one, 0.4, 0.6, it's clear that each tick here, big tick, is 0.1. Now, I go all the way up to 150 for my applied force. So with 10 ticks, maybe I'm going to have 150 at the very top here. So then each tick is going to represent 15, or every second tick is going to represent 30. This is what I'm going to choose for my scale here. This is what I find is the easiest. But at the end of the day, you choose your own scale that you're comfortable to work with. Just make sure that you take up most of the graphing space. We usually encourage you to take up 2/3 of the space. So let's start plotting these points. So what we have here is we have the point 0, 0. Okay. So we got 0, 0. We have point 10 and 20. Oh, it's going to be somewhere in here. Again, we're not looking for exactness. Things are going to happen. You're not going to get it exactly right. So we got 45, so I probably got 0.50. 50 here. I got 0.30 and 80. So we are going to go 75. Really should have given better values for the work for the scale. 0.40, we're going up to 95. So there's 90, 93, 95 is roughly there. And then 0.5, we have 130. So we're going up to 120. 129, 130 will be about there roughly, and then lastly 0.6, we're going all the way up to 150. So we're going to have something that looks like this. Now, is it perfectly linear? No, then that's fine. In real science, linear relationships, we're not going to get it to be perfectly linear. Now, in order to find the value for the spring constant or the elastic constant, we are going to need to find the slope. We need to draw a line of best fit. So what we'd like to do is we'd like to draw that line that captures the trend of these data points. So if I draw something that looks, let's see, I think this looks good. Now keep in mind, we will have slightly different lines of best fit. That's okay, as long as we're close to one another, we're doing fine. The big thing though, and a lot of students want to do this, they know in theory it should go through the origin, and then they're going to force their line through the origin. Don't force it through the origin. If it doesn't go exactly through the origin, that's fine. It just tells us that there's a presence of what we call a systematic error in the system. That's fine. We expect that in real science. So mine doesn't go quite through the origin. It's close to the origin, so that's at least good. If if the expected y-intercept is 0 and you're close to it, you're probably doing fine. If it's way off, that should be sending out the alarm bells. So we need to find the slope of this line. We want to pick 2 points that we can easily identify on this line in order to determine the slope. Again, we will all probably have different points, but we should get close to the slope. So for me, I have this point here, which is going to be 0.16 meters and 36 newtons. And then up here, what do I have? I have this point here. So that is the point, 0.54 meters and 135 newtons. So I have my 2 points on this line of best fit. So you know this could be my x1, my y1, my x2, and y2. So this is going to allow me to calculate the slope. So we know that the slope is just going to be y2 minus y1 over x2 minus x1. So let's calculate that slope. For those of you that are a little bit more advanced with the calculators, especially if you've done, I believe, Math 30-2, you will have learned how to actually get the value for the slope and the line of best fit on your calculator. If you know how to do that, that is also a great trick. It certainly will do a better job than humans can, but you know, right now we're just going to show you the more, we'll call it labor intensive method. So I do that, and from this I'm going to get 261 roughly, and then I have newtons up top, I have meters in the bottom, so I'm going to have newtons per meter, which is the expected units for the spring constant. So I could say the spring constant's roughly 261 newtons per meter, which is pretty good. If you do this in the calculator and you get the exact slope of the line of best fit, like based on, you know, mathematical rigor and such, I believe the actual answer is around 255 newtons per meter. So getting 261, we're doing good. If you're getting close to 255, you know, you're doing excellent. You don't have to get exactly what I have. We're all going to get slightly different numbers because we're going to pick different points on the line. We're going to draw slightly different lines. It's all good. As long as you're close to the actual answer, you are doing fine. So the last little thing, and this is just more of a technical point with Hooke's law. And this has to deal with Hooke's law and Newton's third law. When we talked about F equals kx, the force we've talked about is the force that we supply to the elastic object. So if I pull on this elastic, when I'm talking about Hooke's law, what we've talked about, we're talking about the force that I've supplied. But generally, we want to think about what's happening with the spring or the elastic material itself. We know by Newton's third law, if I pull on this elastic material, it will also pull back on me with an equal force, just in the opposite direction. At the end of the day, elastic objects do not like being displaced from equilibrium. They will always try to go back to equilibrium. So that force that's going to bring them back there, this is what we refer to as the restoring force. And it is always, with exception, opposite to the direction of the displacement. So for example, this person, they're applying this force to the right on this system, this spring. Now, at the same time, they're pulling with this force to the right. By Newton's third law, there will be an equal force and magnitude in opposite direction. So this force here, this restoring force, this is from the spring. This is trying to get this thing back to equilibrium. So this is going to be directed opposite to my applied force, and it's also going to be directed opposite to my displacement from equilibrium. So if we were to write Hooke's law properly, Hooke's law should actually look like this. It should look like F equals negative kx. Because the force here, in this context, this is actually the restoring force. So we are actually looking at F equals negative kx from the perspective of the spring. So we're looking at the force that the spring applies on the object that is pulling it. So in this case up here, we're looking at the restoring force the spring provides on the hand that's pulling it away. So on a data sheet, you will see F equals negative kx. You won't see F equals kx. F equals kx is if the force is the applied force that you're looking at, so the one that you actually supply. So let's look at this question really quickly. So we have a spring. It has a spring constant of 85 newtons per meter. The spring has a restoring force of 25 newtons to the right. So we want to find out how far from equilibrium the spring is displaced. All right, so let's call for this right. Let's call it positive. So we know from Hooke's law, we know the force is just negative kx, and we'd like to find the displacement from equilibrium. So x is going to be the negative of this force divided by k. Well, my force, we're told it's rightwards, so we don't have to put in that negative. We'll leave this negative here, and then that's going to be the negative of positive 25 newtons, and then we have that spring constant of 85 newtons per meter. So what this is going to give is this is going to give how far this is displaced from equilibrium. So we're going to get 0.294 meters. Now the negative is telling us the direction. This thing is going, we've called positive right. So what that's telling us here is that we are going left. That's expected in Hooke's law. We want the restoring force and the displacement to be in opposite directions. We're told the restoring force is right, displacement has to be left. So the last thing we can say is that the displacement of this spring, it's 0.294 meters, and it's going to the left.